Got something going on with my throat. I've got 2 more hours to get going, so work with it a little bit. My name is Jeremy Smith with Lundeca. Lundeca is a company that's based out of Miami, and we do shaft alignment, some vibration analysis in the past, and now ultrasonic or ultrasound, leak detection, things along that line. But today we're going to talk about shaft alignment. We've done shaft alignment since 1982. I have a few cards. The rest of my cards are in my truck, which I figured out about 5 minutes before you guys got here. So if any of you guys need a card in particular, I'll hand it to you. If you have any questions along the way, we're more than happy to help. You just remember the name Lundeca. Again, you can call anybody down in Miami. We're willing to help you guys to learn to understand what you're in your future endeavors. Everyone in here is reliability engineering, pretty much. Okay. So what about shaft alignment? You may have any experience learning about shaft alignment. What is shaft alignment? It's an interactive class. When we say shaft alignment, it sounds pretty intuitive, but what do we mean by that? What's that? Okay, so this is a simulator. We're going to say one of these is going to be a motor and the other side is going to be a pump. Okay, so typically we have a motor, which is the driver, and a driven piece of equipment, which is commonly a pump or fan or things along that line, right? A lot of times these things will mount on a base in a horizontal manner. Okay? And each of these has a shaft that comes out, right? And these shafts meet together with a coupling element quite often. And in our situation, when we line up the shaft, it's pretty much the way that it has to be. Right? So when we just take a straight base, we put a motor, we put a pump on there, we put the bolts through, there is typically going to be a misalignment. Take the center of the shafts of each of these two, the center line, you want these two to be what we call collinear. Okay? Collinear is obviously basically represent exactly the same line as you would think. Now, do we have to be perfect 0, 0 at that point? The answer is no. We don't have to be. We have certain tolerances that we build. But the type of misalignment we have would be horizontal and vertical. Okay, those are the positions. What type of alignment do we have from there? Anybody know? Discussion. No, because he came up to one of my work booths one time and explained it to me. Did you see an offset, a straight up offset, vertical, horizontal? What about something else? What would be another type? Here we go. Angularity. That's right. So we have offset and angularity in this alignment. Now, when we say shaft alignment, we talk about taking the center lines of two shafts and making them collinear at the point of transmission, which is the coupling, under operating conditions. Now, under the operating conditions is another very important component of shaft alignment, because we can take these two shafts in room temperature, ambient temperature, and we can make them 0, 0, completely collinear. What happens if we start it up and we've got really, really hot water running through that pump? What happens to that pump? It gets hot. What about the molecules, the particles in that thing? What do when they get hot? They expand, that's right. Okay, so now thermodynamics. When they expand, they don't necessarily just expand up, but when they do expand, they are taking the center line of those bearings as a result of the housing. And there's typically a few things that result in that expansion. Is the distance from the shaft down to the base, okay? The temperature delta, and the type of material. Okay, that's going to be a coefficient of expansion. So all these different things come there. Now there are other components besides the temperature. There's mechanical changes. The way the pump may be connected to piping and processes coming through. Long story short, this pump can move. And it can get to the point where it moves out of tolerance. So no matter how close you got that, when this thing starts, it'll move out of tolerance, and the pump can still, the pump bearings and the seals can still fail as a result of misalignment. We have ways of measuring that. We have ways of measuring that mechanical movement over time. So we can measure ambient condition, and then we can measure it as its typical running condition. The difference between those we can put in as a thermal component or as a movement component. So we misalign it, Okay, we misalign it cold, so when it runs and everything moves over time and stabilizes, it comes right back into shape. Okay? We've actually seen that several times. There's one facility, the Bowater, Resolute Forest Products. You guys been through there, it's got that terrible smell. They spent $150,000 to $200,000, okay, about every 3 or 4 months to try to figure out what those targets were to get to so they could misalign it. Okay, they got it wrong. You know how they figured it out? Trial and error. We have ways of measuring that with lasers. Talk about tolerances real quick. Again, we said we don't have to be at 0, 0. Bearing manufacturers have a minimal tolerances that they require, and typically that's what we try to do, stay within those bearing tolerances. That's usually a tighter tolerance than a seal or a couple. And those are typical of the 3 components that we're concerned with when we're looking at shaft alignment, okay, to protect. We want to make sure that the bearings, the shaft seals, and the coupling elements will not fail as a result of this alignment. That's the parts we're taking care of. Let me give you a misnomer, okay, that a lot of people will say. There are coupling elements, coupling element companies, more importantly, coupling alignment sales guys that will come to the companies and they'll propose if you have not a particular type of coupling element, it handles more gross misalignment. So if you use it, your pumps and motors are going to last longer. Okay? There's no bearing manufacturer, no seal manufacturer that's going to go on. We have a tolerance and it's based on RPM that we want to stay within, and I'll talk about that in just a second. So do away with that myth. Typically the tolerances of a coupling element, we want to attribute that to stacked tolerances. When you look at a shaft, okay, there's a certain tolerance, plus or minus, when a shaft is made. Okay? When you look at the housing, there's a plus or minus certain tolerances. The bearings, the base, these are all tolerances, and if you stack those up together, that's what the coupling element is meant to take care of. So in shaft alignment, we want to make sure we stay within those tolerances. And the big tolerance we have is RPM. Okay? The vibration guys look at this pretty closely as well. At 1800 RPMs, you may have a tolerance, we'll just look at the offset of, say, 3 thousandths. You want to be less than 3 thousandths at 1800 RPM. At 3600 RPM, we want that tolerance to be tighter or looser. Tighter. Why is that? Why is that? Why do we want that to be tighter? Double the RPM, which does what? Increases the force, right? Okay, increases the force. It also causes that force to hit twice as often. So if you have an impact, because here's the thing, when you have 2 shafts, if they were completely, if you plotted the center line, they were completely in perfect alignment, what would that plot look like? Look like a dot, right? It's a perfect alignment. As things become out of alignment, especially angular, okay, that dot starts to move, and it doesn't move in a perfect circle. The more angularity you have, the more ovality you have. Okay? Literally more ovality. And in that ovality, obviously, you're changing speed, and that changing the speed creates impacts, right? So at 1800 RPM, you may have exaggerate a little bit. At 3600, you would have twice the amount of force. A lot of the shaft alignment capabilities, so let me talk about this real quick, and I'll work into what I was about to say with the lasers. A lot of this, when we talk about shaft alignment, there's several different ways to align a shaft to a pump. One way would be, the most common would be line of sight. Okay? Just that kind of take a look at it to see how things measure. Line of sight to get as much as you can in your eye. Another way would be a straight edge. You can put a straight edge on the 2 shafts. Try to get as close as you can to the straight edge. Okay? In fact, that's a great, fantastic way to get one rough line with a straight edge. What would be another way? What's that? Laser alignment, okay? And another one would be dial indicators. So in order, of sight was quickest and the least accurate. Straight edge would be next, and then dial indicators. Dial indicators we would measure on one shaft, and we could measure the outside of that shaft or even coupling the other shaft, and then the face up. That's a common one. Reverse dial indicator would be another. There's some pretty sophisticated components that goes in there, and if someone's really, really good at using the dials, can get a very precise alignment. Then we step up to the lasers. Lasers were created, brought to the market for shaft alignment in 1982. It's a very crude thing. In fact, it was an invisible beam. You had to have a beam finder. You find out you have this little wand, and then as you move on down, you had to continue finding that thing to see where it was. Well, now we'll have visible lasers. I don't know how many guys can see that, but that's the laser that we have today. Much brighter than even the visible lasers that we had even 5 years ago. Okay. The laser take the reverse dial indicator method, and I don't know if you guys cover that in your classes. If you do, it's very similar math, reverse dial indicator, what we do with laser shaft alignment. We'll take that, and I'll do a drawing here in a second, kind of go over how it thinks. But what we're able to do with it is put in those tolerances. So if you put in simply 1800 RPM, we're going to tell you what tolerance that you need to have. So you don't have to contact the bearing manufacturers. You don't have to contact. You don't have to do the math yourself. It's pretty much put in there. You can also put your own tolerances. Say, you know what? I want to be tighter than the tolerances you're giving. Even though the tolerances you have are never going to fail, you still want to go a little on top. So, anybody have any questions so far? I'm covering a lot of stuff in a short period of time. If you have any questions, just stop me as we go along. If you get the feeling I can talk about this for 4 hours, you're probably right. So let me represent something real quick. We'll say, typically, when you're aligning 2 shafts, you have to have a stationary piece of equipment. And that's your baseline. Okay? You start moving everything both directions, you don't have a point of reference. So by default, you have one side that's going to be your stationary. Most laser companies are going to have your left piece of equipment is going to be your stationary. Okay? Oftentimes it could be the pump, but typically your left piece of machine is your stationary. That's your baseline. So the center line of that shaft would extend out. Again, would represent your baseline. Okay? The movable piece of equipment on the right-hand side, it's going to have the same thing. And we can be, again, we can be high, we can be low, we can be angular, we can be high at this angle, just all kinds of different combinations, okay? And that's just on vertical. When we look at these, we're looking at clock positions. Across the board, whether you're using dial indicators or anybody's laser shaft alignment equipment, we're looking at clock positions. You're looking at 12, 3, 6, and 9 o'clock. Some will call 12 and 3 positive, some will call that negative, things along that line. But what it is the face of this couple, from the stationary side, that's going to be clock. So 12, 3, 6, and 9 o'clock. That way we can have a point of reference of where we are, if we're low and high, and where these laser alignment. The laser alignment, once we take a measurement, so we have a laser and we have a receiver. The laser is going to receive, the receiver is going to receive a laser, and it's going to tell it the approximation of where the things, and it's a PSD, which is a positional sensing detector or something along that line. And depending on how the laser comes in, it's going to pick up where that is, and it sends out a signal, a voltage signal, which we then transfer over to positioning, typically in thousands of nibbles. Okay? We take these, there's several ways to do it. Commonly, it's 3 positions. We can take it at, so if I'm at this position, and this is my clock, would that be 3 o'clock or 9 o'clock? Okay? So if I'm looking this way, that's going to be 3 o'clock. A lot of times it's 3 o'clock, 12, 9 o'clock. If I take those 3 readings, I get a pretty good representation of the way those 2 shafts relate to one another going, once I have that, what can I do with it? The laser's going to tell me how many shims to put underneath my feet to lift it up, to take care of my offset and angularity. Then, okay, it's going to tell me how far to move it side to side to get rid of my misalignment in horizontal fashion. It's going to give me arrows. And as I get closer to numbers, it's going to give me numbers. As I get closer, those numbers are going to get smaller until I get close. Oftentimes, based on your tolerance, they can give you a small, an okay to a smiley face, or simply give you a green light and say, yes, you're within tolerance. Okay? Then you lock it down. You can get a report as a result of this. I'll give you a little bit of insight into the top of that. This is just a very basic aspect of it. If I go ahead and draw I think it's pretty rough misaligned. It's basic geometry that we're looking at. If we look at, say, this is the center line where the coupling element will be, you guys see that this is two shafts with the coupling elements. Everyone see that? Okay. We're going to represent the offset as just simple offset. The angularity we represent as gap. It is the distance between here to here at a certain distance of coupling in a couple of inches. Coupling inches were simply measured from the bottom of the coupling up to the top. Okay? The geometry that we're talking about, we can measure this angle. Whatever this angle is, okay? Because we have, and I can't remember what it's called, you guys can help me, but because we have a perpendicular line here, and that's our baseline going out forward, this angle and this angle, okay, which would be the representation of our misalignment, are the same two angles. So if we know what this angle is, we can know what that angle is. Now, why does that make a difference? This is 12 o'clock. This is 6 o'clock. This moment is equipment. Why does that make a difference? Because if I know what this angle is, watch this. To know what that gap, we'll say we measure up 10 inches on this coupling. At 10 inches, measure the coupling. That gap, let's say that gap is 10 thousandths. Okay? That's 10 inches. That's 10 thousandths of gap per 10 inches of coupling. If I went up and measured 20 inches, what would that number be? 20 thousandths, right? Okay? That's just a representation of things. Now, where that's going to make a difference is when we say that that angle is the same as this angle. If I go from the center line of this coupling and I measure out, we'll say that front foot is 15 inches. If I'm 10 thousandths per 10 inches of coupling, and I'm 15 inches to that first foot, how many thousandths am I off from the center line down to that foot? 15 thousandths. If I measure out to this back foot, I'm 30 inches. How many thousandths am I out there? 30 thousandths. So if I put in the proper measurements, and guess what? The laser's going to ask for certain measurements. It's going to ask from the center of the coupling to the front foot, from the center of the coupling to the back foot, right? Then it's going to ask from the center of the coupling to the sensor. It's got to know what these measurements are so it can tell you what to do with these measurements we just took. So it's going to tell you how far to move those feet in a shimmy manner and also a side-to-side manner in order to get the, everything into alignment. Any questions on that? How are we doing on time? Including questions? So we're 15 minutes in?
Yes.
Okay. I'll say this real quick. Here's some different, these things turn off on me. We also have shiv alignment that we can do. This would be a tool. We take a beam, put it to a sensor, we can look at the pulley. We can line up the pulley. So if we have belts, you can imagine we also want the pulleys and all those kind of things to line up where they can be, right? Technology has continued to advance. This is where technology has been for a little while. We have a typical screen with a display and buttons on the side to push. Okay? This one is not going to come up for me. I charged it, but it didn't seem to take the charge. This is a touch screen. This is where people start to go with the touch screen. Now, can you see why touch screen may not be the best idea for shaft alignment? Because out in the field, you've got people with gloves and dirty fingers. Okay? However, that's the direction things are going at this point. Screens have gotten much better, much more resilient to scratches and much more resilient to dropping and things like that. Any questions? Again, we covered a lot of stuff in a short period of time. Yes, sir.
I've got a question. So shaft alignment, we've established that it's fairly important, but what might be like a dollar amount
It's hard. That's a great question.
like say there are some shafts out of alignment, like how many man hours, how much is a new shaft going to cost to replace for maybe a large motor, like a several hundred horsepower motor, like a giant motor, huge.
I don't get so much into the cost of that.
Okay.
If you're having to take one down, the cost of repairing is very minimal, as you guys have learned. Downtime. Unscheduled downtime is the absolute worst. And that's kind of beyond the scope of this class. We fit within the uptime elements, okay, of shaft alignment, vibration analysis, things like that. When you're talking about importance, and you're talking about low-hanging fruit in a reliability program, lubrication takes care of a great majority of taking care of your bearings, okay? Shaft alignment is another. You have to have the shafts aligned. You have to have things properly lubricated. You don't have those two things, you are going to fail in your bearings. And there's a high amount of people in reliability, people grab a hold of, they say that, I don't know, I've heard even 75 to 90% of all bearings don't go to their intended lifespan. And again, the biggest part of that is the lubrication and shaft alignment. So you've got to be on top of these things. It's not if, it's you have to. Yes, sir.
I just mentioned that in the 90s there was a number of studies done about the cost of alignment because the machine won't shake for free, was the idea. And those were done here at the University of Tennessee, and they were not necessarily conclusive, but there was some questions that they needed more research and such. But overall, it's generally accepted that you save money by having properly aligned machines.
As a result of reduced horsepower?
Reduced horsepower, obviously things like destroying bearings. For a reliability engineer, what you might want to do if you're going out in the industry is take a look at your couplings and the history on them. And are you replacing couplings a lot on certain machine sets? And if you are, there's an opportunity there for reduction in cost and doing a proper alignment or finding out what's going on in the machines, okay?
And I would definitely say, just because there's a maintenance budget, to take a machine down every 3 months to replace a coupling on and a bearing or a seal, don't accept that as the case, that's the way it has to be. Things are designed to run longer than that, okay? It's about the low-hanging fruit. So I say good luck to you guys. It's exciting to see a lot of people come into the reliability field. That's the world I live in. And if there's anything we can do in the future to help you guys, we're here. Good luck to you.